Here's our second example. We have a point particle of charge positive 7 coulombs placed at the origin. 7 coulombs is a large amount of charge. Typical units are actually millicoulombs or microcoulombs or nanocoulombs, but we'll make the numbers easy. So it's positive 7 coulombs of charge. Part A asks what is the strength and direction of the electric field at the point x equals positive 4 meters. And part B asks a second point particle of charge Q2 equals negative 3 coulombs is placed at that position of x equals plus 4 meters, while the position of the first charge remains fixed. And we want to know what the net electric force on that second charge is. So, a reminder first that the electric field around a positive point charge like this will point radially away in all directions. But we're only going to concern ourselves with the x-axis here. And so we're going to specifically look how strong and in what direction is the electric field due to, we'll call this one Q1. Maybe I'll get a different color there to differentiate it. We'll call this Q1. How strong and in what direction is the electric field due to charge? Oh, hold on a second. Draw. There we go. How strong and in what direction is the electric field at this point due to charge 1? So that's the first question. And the second question is what happens when we place a second charge in that field. So some terminology, we are going to choose to call charge 1 the source of the field. So this point particle is our source. This is somewhat of an arbitrary choice, but we're going to choose. So we're going to look at its electric field. So we're considering it the source. Then the second point particle, for our purposes, we are going to consider the test charge. It is the test charge because it's the one that's being brought into the field of the first one. We could probably reverse the roles where this second charge is our source and we compute its electric field, and then we bring the first point particle into that field, but that's not what we're doing here. So let's answer point A. The direction of the electric field, well, it points radially away. If we place a positive test charge at this point, there's no charge here. It's an empty point in space. But if we did place a positive test charge there, it would feel a force to the right. So the direction of that electric field is to the right. How strong is it? Well, the electric field due to a point charge, so this is E from charge 1, is going to be K times the charge 1 times the distance from that charge squared. K is 9.0 times 10 to the 9 in units that you don't really care about, but it'd be newtons times meters squared over coulombs squared. Q1 we said was 7 coulombs. We're going to ignore the sign and we'll use our brain to figure out things like direction. And the distance was 4 meters squared. And if I plug all of that into a calculator, what I end up with is, give me a second to actually do that. We've got 9e9 multiplied by 7 divided by 4 squared, which is 16. And I got, what is that? It's a really big number. Which 7 coulombs is a lot of charge, so we expect that. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I got 3.94 times 10 to the 9th is what I got, newtons per coulomb. Let's check those units real quick. Meters squared will cancel with meters squared. Coulombs squared, one of those two will cancel with this coulombs. We're left the newton per coulomb overall. So those units check out. So we've got the strength and direction of that electric field. Next, B. We want to ask how strong would the electric force be for a negative charge of negative 3 coulombs placed at that point. We could go and now plug in K, Q1, Q2 over R squared, but we're not going to. The reason we're not going to is because we already computed the electric field at that point. So we might as well use the electric force is going to be the test charge Q2 multiplied by the electric field from point particle 1. And so this would be the electric force by 1 on 2. And we know that because we're looking at charge 2. So anyways, that's going to be, did I say 7 or 3 for that one? That one's 3, sorry. 3 coulombs multiplied by my 3.94 times 10 to the 9th newtons per coulomb. And the electric force that 1 exerts on 2 is going to be that number times 3. Its magnitude, therefore, is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11.8 times 10 to the 9th newtons per coulomb. So 11.8, what would that be? Billion? A very large force. And this would just be newtons because it's the force. And we took coulombs canceled with per coulomb there. Probably an impossibly large force. But you get the idea. And you can check my math to see if I missed something there. All right, so that's the idea. And then the electric force in which direction is a negative charge. So the direction is in the opposite direction of the field. Opposite direction of the electric field due to charge 1. So direction is left. So it's to the left. All right, that answers our 2 questions. Hopefully that helps out. We can look at determining the electric field strength at a particular point first, and then we can use that electric field strength and see how a second particle interacts with the field from the first. If you have any questions for me, please let me know.